Well, good evening, everyone. Michael, soothing here. I hope you had a great New Year's Eve and a good 2020 coming up. Here we are, the first work day back from the 2-week break, or 1-week break, or however many days off you had. I thought what we would talk about today is the wonder of ice cubes. I have my metal straw here so as to be completely environmentally conscious. Right? See there? Oh, I can see you through the straw tube, through this metal tube. You have to be careful with these because, a lady was killed by one. I won't give you the details in case you just are having your dinner or something. I have 2 glasses with ice because I'm going to put some A&W in one, diet A&W, because I have to be careful about sugar. It's not as good as that big frosty mug they give you when you go to the A&W, restaurant, but it's still pretty good. Then I have one for spring water here. Spring water. This is too big. And this video was requested by one of my favorite subbies. So actually I've had multiple requests for ice cubes. But anyway, for a repeat. So we're going to do that. And I'm going to discuss also some characteristics about the globe, the earth that we live on. And you flat earthers might want to watch something else because you only believe in the, the made up stuff, that we live on a pancake. But anyway, I'm going to discuss some of the amazing design characteristics of the globe that we live on. Do you like this globe? It's all kind of semi-precious stone inlay stuff. So it's kind of pretty one there. It's all stone of various types. I'll hold it back here where you can see it better. The whole thing. Take a trip around. Flat earthers say, why don't you fly off the globe if it's spinning, so many thousand miles an hour? The reason you don't fly off, besides gravity, is that it's moving so slow. Imagine you're a magnet held on by gravity, right? This is the speed that the globe is turning right now, relatively speaking, to make one revolution in 24 hours. Can you see it? It's spinning that fast. To make one revolution in 24 hours. That's what you would see if you were looking from space. So, one of their silly arguments, but we're not here for that. We're here to hear ice cubes. But first we need to pour our liquid in. So let's see what it sounds like. Will we get any carbon dioxide swish sound? Oh, we did. It's a bit loud. But we got that. I'm going to let you hear the little bubbles when I pour it into this glass right here. I'm going to hold it by the test cam so you can hear it. Ooh, you can hear those bubbles really good. I'll go ear to ear with it. A little bit here, a little bit over here. We'll mix those with the chopstick here. This chopstick right here. Now I have a refreshing beverage that I can imbibe in while we talk about the amazing characteristics of the Earth. I'll take a sip of that. I love cold A&W root beer, but I can't drink too much of it at once, because then I would have to edit out a burp, wouldn't I? We don't want to build up any pressure or add to global warming too much by stirring that CO2 around in there. Now we'll put some spring water in the other glass. They call this in Filipino tubig. Tubig. I could make a joke about that, but I won't, because this is a family channel. Ooh, that looks refreshing also. Some nice cold. Let's see what this sounds like if we go from one side to the other. I'm a little warm because I just got done exercising, so I need a sip of this through the metal straw. Oh, but I don't like the sound it makes when it squeaks on the glass. So I'm going to remove the metal straw from that one and replace it with the chopstick. Now I have a trace in here of root beer, but it's just a tiny, tiny bit. I know if I was listening to this, which I will at some point, I never listen to my own videos. Even when I edit, I don't really do post-production editing, because I don't like my videos to ever be inauthentic or contrived or gimmicky. So what I do is I pretty much run it uncut, unless there's a really loud bang or something outside that I have to remove, like, one of the neighbors is shooting their spouse or something, then I might cut that out. But any loud screams. Let's see, I thought I would chat about the incredible design of the Earth and our solar system a little bit. And while I'm reading it, I'm going to continue to mess with these ice cubes. The universe, our galaxy, our solar system, and the Earth-Moon double planet system demonstrate some remarkable evidence of design. Taken separately, each characteristic is highly improbable by random chance, but taken together, the probability of all these characteristics is so small as to virtually be impossible by random chance. The alternative would be that there is a designer. All right, let's look at a few of those characteristics. The sun and our solar system have been located in a stable orbit within our galaxy for the last 4.5 billion years. This orbit lies far enough from the center of the galaxy and between the spiral arms, far from, I should say, the center of the galaxy, and between spiral arms. If you were right in the middle of a spiral arm, you wouldn't be able to see much in the night sky but white, because there's so many stars there. It would be a blur, by the way. The stability of our position is possible because the sun is one of the rare stars that lies within the galactic co-rotation radius. Typically, this is going to go on for a while and is a bit too technical unless you're really into astronomy. So I'm gonna go down to some other characteristics that we can talk about. The unique stabilization of the inner solar system. A recent study reveals some unusual design in our solar system. With the continuing growth in the capabilities and sophistication of computer systems, scientists are gaining the ability to model the dynamics of the solar system. Okay, there's a long technical explanation, which I'll again skip, but the bottom line is we absolutely need, in order for life on Earth to exist as it is, we absolutely needed a solar system just like ours, with the large gas giants, Jupiter and Saturn, out there in the outer rings of rotation. Not rotation, but revolution around the sun. And, rotation around the sun. Get it right. Okay. They clean up all the really bad cosmic debris left over from the formation of the solar system, and things like big asteroids and comets. They're sucked into places like Jupiter and Saturn so that they don't come into the inner solar system and bombard the Earth the way it was happening in the early part of the solar system's formation. Without those gas giants, we'd get hit by large pieces of debris that would wipe out all the life on Earth. Which, by the way, there's still a small chance that could happen, but it's about 1/1000th as what it would be if say Jupiter was not there. I need a sip from my ice cubes. I think what I'll do, instead of just flat reading all of these paragraphs, which are quite long, a lot of this comes from a book called The Privileged Planet, which is a scientific exploration of all of these fine-tuned parameters for Earth, the solar system, and the universe, the galaxy as well. But I have here a short list of some of these things that I can read to you a little bit while we stir our ice cubes around. And this is characteristics where I can just give you the summation or the summary of what would be bad if these didn't exist exactly as they are. Galaxy size, for example. If the galaxy was larger, the infusion of gas and stars would disturb the sun's orbit and ignite deadly galactic eruptions. Don't you hate it when there's galactic eruptions? I've always hated that myself. If the galaxy was too small, there would be infusion of gas insufficient to sustain star formation long enough for life to form. That's galaxy size. Galaxy type. If the galaxy is too elliptical, star formation would cease before sufficient heavy elements formed for life chemistry. If it was too irregular, radiation exposure would be too severe at times, and life-essential heavy elements would not form. Do you know the life-permitting elements, the elements that we have from the table of elements, came from exploding stars? Yes. Someday maybe we'll discuss how that works. But basically all the even elements like gold and silver, platinum, palladium, which I invest in, by the way, in my portfolio, especially some of the companies that mine them, those elements came from the stars. Crosby, Stills, and Nash, in their famous song Woodstock — I should do a video on Woodstock sometime for you younger people that don't know what that is. Anyway, one of their famous lyrics are, "We are stardust, we are golden, we are caught in the devil's parlor." Okay, and in a way there's a literal truth to that, because stardust is the stuff that formed the elements on the earth from which we were formed. When God says in Genesis, Adam was formed from the dust of the earth, that in some sense is literally true. Those elements came from the stars and became the dust of the earth, from which us carbon-based life forms could eventually come to be. Now, what else? Galaxy location. If too close to a dense galaxy cluster, our galaxy would be gravitationally unstable. If too close, okay. I don't want to get into the really technical ones. Let's talk about supernova eruptions. Another thing that I don't like to see happen too close by. It's kind of like if a stick of dynamite goes off and you're a mile away, you can hear the bang and see the cloud of dirt fly in the air. And that's fine. But if you're standing next to the stick of dynamite, well, then you get a different result. That, if I was standing next to a stick of dynamite, and it exploded, then you would know what color eyes I have. You would know I had blue eyes, because one blew this way and one blew that way, okay? But I don't want it to be like that, so I won't stand. Now, if you were too close to a supernova, radiation would exterminate all life. But if you're too far from supernovas, then the star dust would not be available for the rocky planets to form. If the supernovas were too infrequent or too frequent, you would get the same bad results of each type. If they happened too soon, too little ash would be available for rocky planets to form, and if too late, radiation would exterminate all life. So, white dwarf binaries. If there were too few, then insufficient fluorine would exist for life chemistry. If too many, the orbits of life-supportable planets would be disrupted, and life would be exterminated. Proximity of... I wish the refrigerator would cease and desist. I gotta start moving my ice cubes again so that you have a more pleasant sound to listen to. I'm going to skip some of these really exotic things about how the solar system and galaxy is fine-tuned for life here on Earth, and skip down to some that are a little more obvious. Because there are several more that are quite technical. Parent star distance, that's our sun, from the closest spiral arm of the galaxy. If that distance was too small, radiation from other stars would be too intense, and the stellar density would disturb the orbits of life-supportable planets, i.e., Earth. But if too far, then the quantity of heavy elements would be insufficient in our solar system to form life-supporting planets. Z-axis range of star orbit. I'm going to skip that one. Number of stars in the planetary system. If there were more than one star in our solar system, tidal interaction, because many systems are binary, two stars together. If more than one, tidal interactions would make the orbits of life-supportable planets too unstable for life. In other words, you'd have giant earthquakes every few minutes. Well, maybe not every few minutes, but frequently. Or you would have hot molten magma on the surface because of all the pulling from the two stars be too strong. But if you didn't have a star in a planetary system, then you wouldn't have a heat source, of course. Parent star birth date. Onions. If more recent, star burning would be unstable. In other words, if we came along at the wrong time, stellar system would contain too many heavy elements for life chemistry. If less recent, the stellar system would contain insufficient elements for life chemistry. Parent star mass. That's the sun we're talking about again. If it was larger, the star's luminosity would be too erratic, and the star would burn up too quickly to support life. But if it had a smaller mass, the life support zone would be too narrow. The rotation period of life supporting planet like ours would be too long, and UV radiation would be insufficient for photosynthesis, which is how plants grow. They need the sun and they need carbon dioxide. CO2 is plant food, by the way. In case you've heard it was a pollutant, it's actually extremely necessary for all life on Earth, including and especially plant life. Parent star metallicity. This gets in parent. I'm not going to go through that one again. It's too much. Life chemistry couldn't exist. Too little. Radioactivity would be too high for life to exist. And heavy element concentrations too poisonous, like uranium and such, for life here. Parent star color. Have you ever thought about star color? There's stars that are... Have you ever looked at the night sky and realized that some stars are reddish or orange or bright blue or yellow or white? Most look white, but they're... Hold on, I need a sip of the cubes ear to ear. Here, we're going to do some ear to ear with the ice cube here. Like that. And then a sip. I'm not giving you a very good explanation today, but of these things, I'll do a different video where I do a better job someday. But what I'm really trying to do is put you to sleep, so that's okay. How about parent star color we were talking about? If it was more red, photosynthetic response would be insufficient to sustain life. If it was more blue, same result. How about helium production of the star? If too little, simple molecules essential to planet formation and life chemistry would never form. But if too great, planets would form at the wrong time and place for life. Parent star luminosity. If it increases too soon, a runaway greenhouse effect would develop. Uh-oh. And if it increases too late, runaway glaciation would develop. Surface gravity, which governs escape velocity, by the way. If it was stronger, a planet's atmosphere would retain too much ammonia and methane for life. But if it was weaker, the planet's atmosphere would lose too much water for life to exist. This is probably the problem with Mars, by the way. It's a bit further away and a smaller planet. And it may have had water at one time, but the water, dissipated into space because the gravity wasn't quite strong enough to hold it. When you go further in, closer to the sun, well, if you go way out into the solar system where the gas giants exist, they're made up of really nasty gases like ammonia. You wouldn't want to, and methane. You wouldn't want to be trying to breathe that stuff. And they don't have a nice rocky surface, of course, with a breathable or life-permitting atmosphere or water. Distance from the sun. If greater, the planet would be too cold for a stable water cycle. We're in perfect balance when it comes to ice, snow, and water. We have just the right perfect balance so that we get snow in the winter, which can then provide melting water in the summer, etc., and ice in the areas we need it. But then we can have the liquid form of water. This is why I decided to talk about it, was because I was thinking in terms of the balance between snow and ice and water on our planet when I got the request to do a video with ice cubes. So I said, yeah, let's do it. Maybe I better try it. I don't want the root beer to feel left out, do you? It would get sad and lonely if I didn't have any of it and let the ice cubes melt. But there's just something warped about using a metal straw. I can't quite get used to it. All right. And of course, if your planet was closer to the sun, the Earth, it would be too hot to have a stable water cycle. inclination of orbit. Do you know that it's very important for our planet to be tilted on its axis? I explained the reasons why in another video sometime. But, we have this axial tilt, and that's very important for our seasons to exist. And we need those seasons to exist. They're important to sustaining life. If the axial tilt was greater, the surface temperatures on the planet would be differences, between hot and cold in the summer and winter, would be too great to sustain diverse life forms. But if the axial tilt was less, you would have that same result. If the rate of change of axial tilt is greater, then climate and temperature changes would be too extreme. The rotation period of the Earth, the 24-hour rotation, if it was a longer period, temperature differences diurnally would be too great for life. If shorter, then the atmospheric wind velocities would be too great for life to exist. The wind isn't really blowing around the Earth. If you think about wind speed, it's the other way around. The Earth is rotating, and it's kind of sucking the wind, the atmosphere, along with it. So as it rotates, it's pulling the atmosphere along behind it. And the wind is not quite keeping up. And so the wind that you experience blowing against your face is actually the wind's attempt, the atmosphere's attempt to keep up. But it can't quite keep up, so it's always falling behind. And that creates wind currents. Kind of like if you stick a ball in a basin of water and spin it with your finger, for example, the water will start to circulate with it, but not quite at the same speed. It can't keep up. Anyway, if the Earth was spinning faster, wind velocities would be much higher than they are, and everything would blow over, including us, okay? No buildings and no trees, it would all fall, So you think that, 60 or 80 mile per hour winds are high, or say, 120 kilometer per hour, if you're scientifically minded. Imagine 500 kilometer per hour winds, right? Like on some planets that rotate faster. Rate of change in rotation period. I don't want to get into the technical complexity. Planet's age. If your planet is too young, the planet rotates too rapidly for life to exist. It starts its rotation quite fast, and then over billions of years gradually slows down to the 24-hour per day we have now. If it's too old a planet, then the planet's rotating too slowly for life to exist. Nighttime shouldn't be, 4 or 5 months long, right? It would be too cold for plants and too dark. Plants could never survive, nor would we. How about our magnetic field? If it were stronger, electromagnetic storms would be too severe. But if it were weaker, the planetary surface and the ozone layer would be inadequately protected from the solar and stellar radiation that bombards our planet each day. Do you know the magnetic field is part of what protects us? If you've ever seen the Northern Lights, or if you've seen video, which you can look at on YouTube, of the Northern Lights, that's the bombardment of radiation being lit up by our protective ionosphere and magnetic field. We don't want that to go away. Some say the magnetic field could reverse in our lifetime because it periodically does. Every few hundred or 1,000 years, I can't remember now when the last one occurred. You can tell because you can see it in rocks. The age of the rock shows the particles polarized toward the north and some, toward the south and others, depending on the age. So you can go down in layers and see when previous reversals occurred. But thickness of the Earth's crust. If it was greater, the crust would rob the atmosphere of oxygen needed for life. But if it was thinner, then volcanic and tectonic activity would be destructive to life. In other words, we'd have volcanoes everywhere and molten lava every place and giant earthquakes, and tsunamis all over the place that would be far more massive than what we experience now. I need to relax you with these ice cubes so you don't have to think about massive volcanoes and tsunamis, right? And earthquakes. We don't want those. Albedo, which is the ratio of reflected light to the light falling on our surface of the Earth. If that albedo, and that's based on what's on the Earth, water, land, ice at the poles, if that albedo reflectivity was greater, runaway glaciation would develop, and we would just be a giant, the Earth would just be an ice cube. It would look like one of these, just an ice cube, right? But if that albedo, based on the Earth's composition, was less, the runaway greenhouse effect would develop, and we'd be in a hot house of a few hundred degrees. And I don't like it when it's a few hundred degrees. That's not pleasant to me. That would require massive air conditioning, but we wouldn't be around to build it. Asteroid and comet collision rates. If they were greater, the ecosystem balance would be destroyed. But if they were less, the crust of our planet would contain too little of certain life essential elements. See, we needed in the early stages of the Earth's formation and history, we needed lots of bombardment from comets and asteroids, because we needed all those elements and that water, things like that, to be here. But in the late stages of the solar system, you don't want that anymore. The mass of a body colliding with the primordial Earth, if greater, Earth's orbit and form would be too greatly disturbed for life. But if lesser, Earth's atmosphere would be too thick for life to exist, and the moon we have would have been too small to fulfill its life-sustaining role. And by the way, we need the moon to be exactly the size and distance and rotational period that it is from the Earth. It's essential to the tidal activity that we need for sea life, for all the wetlands and marshlands, and the upper tidal zone that's so essential to the ocean life. You need all the little critters to get that mixing of the water every day and nutrients all flowing in to the tidal wetlands and flowing out again. Study the tidal zone sometime, and you'll see why that's essential for our whole ecosystem to exist. There's some other things here about the timing of that early collision that formed the moon and how important that was. The oxygen to nitrogen ratio in the atmosphere. If greater advanced life functions would proceed too rapidly, but if lesser advanced life functions would proceed too slowly. Carbon dioxide level in the atmosphere. If greater, a runaway greenhouse effect would develop, but if less, plants would not be able to maintain efficient photosynthesis. You need a carbon dioxide range that's between about 200 and 700. Right now it's around, I believe, 400. That would be 400 parts per million, by the way, which means carbon dioxide is less than 1,000th of the atmosphere, of our atmosphere. It's about a little less than 1/2 of 1,000th. So, it's not exactly a huge part of the atmosphere, but it's quite necessary. Water vapor quantity in the atmosphere. If we had a lot more water vapor clouds, then a runaway greenhouse effect would develop. And we wouldn't want that. If we had less, we wouldn't have the rain that we need. And the rainfall would be too meager to allow for crops and plants and things like that. Atmospheric electric discharge rate. If it was greater, fires would be too frequent and widespread for life. I saw a bolt of lightning hit a tree in Oregon and start a fire right off the bat once during a big electrical storm. It was interesting. But if we didn't have enough lightning, too little nitrogen would be fixed in the atmosphere. You need to have that nitrogen, by the way. It's important for various things. It has to do with, again, plants and crops. Ozone quantity in the atmosphere. If it was greater, surface temperatures would be too low for life. But if it was insufficient, UV radiation would be too intense for life. And surface temperatures would be too high. So we want the ozone to be there in the right amount. Oxygen quantity. If oxygen in the atmosphere was higher, plants and hydrocarbons would burn up too easily, destabilizing Earth's ecosystem. But if it was less, advanced animals would have too little oxygen to sustain their lives. Seismic activity, that's earthquakes. If it was greater, life would be destroyed because we'd be flying in the air all the time from earthquakes. I actually went through the Loma Prieta quake in Santa Cruz Mountains. It was about 4 miles from the epicenter, and It was strong enough to about throw you off your feet. It was only a 7.0, you know. If seismic activity was less, however, nutrients on ocean floors from river runoff would not be recycled into the continents through plate tectonics, and not enough carbon dioxide would be released from carbonate buildup. In other words, the stuff would get absorbed down into the ocean and never come back. I don't have time to give a whole lecture on plate tectonics, but it's a subject that's interesting to me. Oceans to continent ratio. If greater, the diversity and complexity of life forms would be limited, and if smaller, same result. We have just the right balance of land and ocean to maximize our life forms. Distribution of continents. If too much in the southern hemisphere, sea salt aerosols would be insufficient to stabilize surface temperature and water cycle. I'm going to skip that because I haven't studied it, and I like to verify each thing I read. I haven't verified that one, but I have verified the next one. Frequency and extent of ice ages. If we had less ice ages, Earth's surface would lack the fertile valleys essential for advanced life. Mineral concentrations would be insufficient for advanced life, but if the ice ages were greater, Earth would experience a runaway freezing and become a big ice cube. As we mentioned before, we don't want to live in a big ice cube. Soil mineralization. If nutrient poor compared to now, diversity and complexity of life forms would be limited. But if the nutrients were higher, the same result. Gravitational interaction with the moon. If it were greater, the tidal effect on the oceans, the atmosphere, and the rotational period, because the moon affects our rotation, by the way, would be too severe for life. Imagine if the tides came up like 50 or 100 feet, would wipe everything out like a giant tsunami. If the moon was bigger or closer. But if the gravitational effect was less, then the movement of nutrients and life forms from oceans to continents and vice versa would be insufficient for our life forms, and the magnetic field would be too weak to protect from dangerous radiation. The ice cubes are still fresh. Jupiter's distance and mass. If it was a greater distance, Jupiter would be unable to protect Earth from frequent asteroid and comet collisions. If you want to see an example of how Jupiter protects us from cosmic bullies and acts as our personal bodyguard, look up on YouTube about the comet collision with Jupiter, where it broke it up into pieces and sucked it into its orbit and eliminated it. The giant planets, Jupiter and Saturn, but especially Jupiter, is just the right size, distance, mass, and gravity to pull away from us asteroids and comets that would otherwise come into the inner solar system at too high a rate and mess with us, well, and destroy our Earth at some point. Jupiter's mass, if Jupiter was closer, the gravity would be too high and it would destabilize our orbit around the sun. There are several other things about Jupiter that I won't go into. There's our atmospheric pressure. If smaller pressure, liquid water would evaporate too easily and condense too infrequently to support life. I'm missing a page because my printer ran out of paper. But I had another piece of paper about another printout on the fine-tuning of the universe. This is some of the most amazing stuff ever because the laws of physics that govern our universe are so fine-tuned that they're far beyond any possible random chance statistical possibility, because the tiniest deviation would render our universe and life in it impossible. The ratio of electrons to protons has to be fine-tuned to 1 in 10 to the 37th. If you understand math or scientific notation, that is an enormous number. You can't deviate the tiniest bit. The ratio of the electromagnetic force versus gravity has to be fine-tuned within 1 times 10 to the 40th power. The expansion rate of the universe has to be fine-tuned to 1 in 10 to the 55th power. The mass density of the universe has to be fine-tuned to 1 10 to the 59th power. And finally, the cosmological constant, also known as dark matter, has to be fine-tuned to 1 in 10 to the 120th power. Any of those off at all by a trillionth of a trillionth of a trillionth, and we simply wouldn't be here, nor would our planet or our universe exist in its form. And so, those are some of the interesting things. I'll do a better video on this sometime in the future, where I give you a more scientific explanation, perhaps, or we'll pick just a few rather than trying to run through a summary of all. But now we're running to the end of our useful battery life, as we often do, and so we'll listen to these ice cubes just a little bit more. Ear to ear, around the Tascam, binaural, stereo, microphone, and then I'll have another sip through this dangerous looking metals. You know, this could double as a blowgun now that I look at it. I think some indigenous folks would like to have had a metal one like this back in the old days. Really smooth bore inside and all that. Maybe it should become part of survival gear, you know, along with some darts. I might have to try that. Or it could be a giant pea shooter, perhaps. What do you think? All right. I hope this video relaxed you, because that was its intended purpose. And I hope that I can de-stress you and help you to sleep, or at least relax more, and decouple from the stresses and strains of life that can overwhelm us from time to time. Take care, everyone. Don't ASMR and drive. Bye-bye.